Hi, this is the final exam review for physics, and what I have in front of me, you'd be happy to know, is I have the final exam. Let's look at the final exam and see what we see. Well, we see 80 questions. Now, let's see, from 67 to 80, you're going to be given actual calculations to do. For instance, I'll read you one. That will reduce the frustration. I'll just change the numbers around. It says when a 120 Newton rock is suspended beneath the surface of water, its apparent weight is 60 newtons. What volume of water must therefore be displaced? Well, if it's 120 newtons and it has an apparent weight of 60 newtons, that means that the buoyant force was 60 newtons. Now, you take that buoyant force and you put it into the appropriate equation and you solve for volume. Easy. So that's easy. So, and you know G is going to be 10 meters per second squared or 9.8, whatever you choose. I'll make sure that I acknowledge a range of answers there. A person weighs 650 newtons. What is the mass of the person? That's pretty easy. Let's go to the beginning and look and see what kind of questions we have. Let's see. We have some, looks like velocity questions, but it's really not. It's material that came right out of the test bank on this would be chapter 9. How much farther will a car travel at 100 kilometers per second skid than the same car traveling 50 kilometers per second? So you have to know the equations that go with that in terms of distance and possibly energy. You have a rocket problem, okay, and you need to know, it says rockets are launched from an airplane in the forward direction of motion. The kinetic energy of the plane will be, and then you need to look at the answers there. I have another one, an object at rest may have energy, speed, velocity, momentum, none of the above. If something is at rest, that's a good point. Is it really at rest? Or is rest really what temperature in Kelvin? So, at room temperature, would that object truly be at rest? If in a vacuum on Earth, an object has no mass, heat, temperature, weight, buoyant force. So, what is air? That's the question. Air, we don't think of air as a fluid, but it is. It behaves exactly like water in the ocean. Fluid is fluid. Fluid is anything that flows. For instance, a balloon is buoyed up with a force equal to the blah. Okay? Equal to the blah. So, remember what buoyant force is. Buoyant force is the weight of the volume of fluid displaced by an object. So if something is floating, it's displacing its weight. So the buoyant force, let's say a big battleship. A big battleship will displace tons of water. Well, you could actually measure that if you had some kind of crazy container and you didn't have the ship in the water, and then you put the ship in, and the water would rise. Let's say the water is at a particular level just below these holes in the container. So when you put the ship in, the holes will let the displaced water out, and then I can find then it goes into down into a trough, and that trough, we can find the weight of that trough, and that would be equal to the weight of the ship. So whatever that ship displaces, and it's floating, that's what its buoyant force is going to be. Also, here's another one. If I have a piece of iron, let's say it's 1 cubic meter piece of iron, and I have a 1 cubic meter piece of wood, okay? The wood is obviously lighter, the iron is really heavy. Wood has a density range of about 0.2 to 0.6, maybe, depending on the density of the wood, for instance, oak versus pine, etc. So let's say I have a cubic meter of pine, very light wood, and I have a cubic meter of iron. What has a greater, I put them both in the water, which has a greater buoyant force? The iron or the wood? That's a good one. Okay, here's one. As a high altitude balloon sinks lower and lower into the atmosphere, its volume decreases, weight increases, density increases, mass increases, none of the above, all the above. Did I say increases or decreases? I'm not telling. It's the question that I'm posing you to be most important. I'm not really going to read a lot of answers here. A block of balsa wood floats on water, while a block of lead the same size, meaning volume, lies submerged in the water. The buoyant force is greater on the lead, greater on the wood, same for both. A lot of buoyancy problems in the beginning here. And then I have two forms, though, so they're going to be mixed up, the questions. So I have momentum. Momentum of an object is defined by the object's blah. The reason padded dashboards are used in a car is that they look nice and feel good. I'm going to buy that one. I'm going to buy that car because it has a nice dashboard. Is that why they have nice dashboards? Padded dashboards? What about airbags? What about crumple zones? What about seat belts? What do they do? What do they actually affect? Impulse, possibly. What part of impulse? Time. I'm not saying if that's part of the answer because I'm way beyond that. Here's one. A truck traveling north with a momentum of 2,600 kilometers per second, and a motorcycle heads west with a momentum of 1,500 kilometers per second. The motorcycle hits the truck. If the two vehicles collide and then stick together, what is the momentum and direction traveled? Aha. ... as the plot thickens. ... The mass of a lamb that weighs 110 newtons is about... So easy. I can't believe I'm giving you such an easy final. Okay, here's one. Unit of pressure. I'm on number 52. Tennis ball and a solid steel ball with the same diameter. So you're going to be looking at, now we're on to Newton's laws. Remember, it's Newton's laws. So chapter 3, 6, 7, 8 is momentum, 9 is work, energy, and machines. And then 19 and 20. 19 is liquids and 20 is gas. Remember your gas laws. All right. Block is at rest on an inclined plane. The force of friction necessary to prevent the block from sliding increases when I increase the angle or I decrease the angle. Remember, if you increase that angle so it's vertical, there is no friction, is there? It's free fall. There's air friction, but there's no friction on the board. So what's the answer to that question? A high school student hit. Remember, when they're talking about the friction, remember what the friction is. Friction is the same as P, right? If it's going to slide at a constant velocity, right? Now let's talk about this. I have a block on a plane and it's at an angle, right? So P, if it's going to slide at a constant velocity, P, FP and FF have to be equal and opposite, right? Okay. So as I increase the angle, what's happening to P? Isn't P getting shorter or is it getting longer? What's it becoming? What is P becoming? What is P and N, Fn and Fp? What are they becoming? Remember, Fp and Fn and Ff are values that come from Fw, right? If the plane is horizontal, Fw is all it is. Now I'm converting some of Fw into Fn and Fp. See? Now watch how Fp and Fn will change. Okay, you got it? Very important. Look at the dynamics. Look at the dynamics in FP and FW relative to the board. That's going to be very important for your final. Okay? A high school student hits a nail with a hammer. During the collision, there is a force. Remember, you have Newton's three laws. What's Newton's first law? Inertia. What's Newton's second law? F equals ma. What's Newton's third law? Opposite actions. For every action, there's an equal and opposite reaction. So a student hits a nail, a high school student hits a nail with a hammer during the collision. There is a force on the nail but not on the hammer, on the nail and also on the hammer but not on the nail. Remember, the hammer hits the nail and the nail hits the hammer. Okay? So remember, Jacob, remember, you're playing football. You're going to tackle somebody and that person is tackling you. So you hit the player hits you. Get it? Equal and opposite reactions. Okay. Here's one with the horse. Remember, if a horse pulls a wagon at rest, the wagon pulls back equally on the horse. Can the wagon be set into motion? Remember, I did a whole thing on that lecture on the horse. So break out that page in the book and look at that. If you don't understand that, you can access the lecture that I made on the horse. Okay? Remember the horse. And that's what we'll have to say about this final. The call of this final is Remember the Horse. Okay, I should entitle this Remember the Horse. Okay, let me take a quick break. I'll go back through this and we'll see what we can do. Okay? I hope this is helpful. Okay, I am back. Now, you have lectures that you can look at, and I think that's very important. What I could have done is I could have put into the review some of the questions from the book that are consistent, but I think you should look at the lectures and see where I stress things. So what I'm going to do is I'm going to go back through the exam and not necessarily tell you questions, but give you areas that you can look at. It's very important to look at the lectures. They're a great resource. I know it's a little painful, but you should try doing that anyway. Okay, so you want to look at kinetic energy relative to simple machines. There doesn't seem to be a lot on actual simple machines like various things relative to mechanical advantage, theoretical mechanical advantage, etc. But there seems to be some things about kinetic energy and potential energy. So that's something that you should make it a point to look at. Don't spend a lot of time on my lecture on Chapter 9 relative to machines, but look at it relative to kinetic and potential energy. It also talks about pressure. So you want to look up pressure. What does pressure mean and how does a barometer work? Now let's talk a little bit about air pressure and what I told you. It was the centerpiece of all of atmospheric pressure and gases and buoyant force, etc. The atmosphere has a weight. It has a weight. And what's its weight? Well, if you took a cubic meter of water, that would be 1,000 kilograms. 1,000 liters. So 1 cubic meter has a mass of 1,000 kilograms. Now, I'm not doing the calculation showing you that. I'm giving you that. Okay. So 1 cubic meter is 1,000 kilograms. 1,000 kilograms is 10,000 newtons. Okay. Now, that cubic meter box is sitting on the floor. So the weight is going to be 10,000 newtons on that square meter underneath the box. Now cubic meter, remember, area is square. So it's square meter. So it's going to be 10,000 newtons sitting on the floor. So it'll be 10,000 newtons per square meter. Now, a newton per square meter is a pascal. So that's 10,000 pascals. So now, that's 1 meter. If I stack, so I have 10 of them, That's really heavy. Can you imagine being under that? That would be horrifically heavy. But that's the weight of one atmosphere. The weight of one atmosphere is 10 times 10,000, or 100,000 pascals per square meter. Now, there's a little bit more than that. It's actually 101.3 pascals, but we're not, that's okay. 10,000, 100,000 is fine. So 100,000 pascals, right? So it's 100,000 pascals per that square meter. Well, that's going to be the atmospheric pressure. Now you may ask yourself, well, why don't we feel that weight? Well, there's two things. One, that's how you're built. And that's Newton's third law. You have an action, that pressure pushing against you, and you have a reaction, you pushing against the atmosphere, and it's equal. That's just the way we're put together, the way we evolved. Now, also this. Let's say we know that air, this atmosphere, is a fluid. Us being in the fluid, we have there's a certain buoyant force on us. So if you had a vacuum on the surface of the earth, and you could somehow magically breathe without any kind of apparatus helping you, you would actually weigh more because the fluid is gone. So you would weigh, how much less do you weigh? Well, you weigh your apparent weight, which is in a vacuum, how much you would weigh. And then you would weigh in the atmosphere on the earth, you would weigh that weight minus, your apparent weight would be minus we'll call it the vacuum weight, minus the weight of the volume of fluid that you displace, the weight of the air that you displace. So you're going to weigh something less than a kilo less by being in the air. So somewhere less than a kilo, somewhere less than half a kilo, but it's something. So you'd weigh maybe a pound less-ish, maybe half a pound. You weigh a half a pound more if you were in a vacuum on Earth. So I think that's pretty interesting. But keep in mind that the pressure of a fluid is only dependent upon, I don't want to give you the wrong impression by this box, it's only dependent upon, if I'm underneath the ocean or I'm underneath the atmosphere, it's only dependent upon the height of the fluid, the depth, the height of the fluid. So look at your equation and see that it's the density of the matter that you're in and also your heights. So let your equations do some work for you. All right? Let's bring out some equations and look at them, and then I'll continue with the review. So I'm looking at the equations for fluid dynamics. The pressure of the fluid in, like, say, the bottom of the ocean equals the density of the water times the height of the column times G. And don't forget, the hydrostatic pressure is the air pressure plus the pressure due to the depth of the fluid. Okay, so if you want hydrostatic pressure, you got to make sure you add in the air pressure. Let's see. The weight of an object, the apparent weight, is the weight minus the buoyant force. So if something's floating, the weight of the object equals the buoyant force, and the buoyant force equals, how do you get the buoyant force? Well, that's going to equal the density times the volume times G. You should also know your other mechanics equations for velocity and weight. That board, you should put as much of that on there as you can, because remember, mechanics is the marriage between motion and force. So even though it may seem old, where we did it in chapter 4, motion, you still have to know that stuff in order to answer questions later on in chapter 6, for instance, 6 and 7, and also 8 and 9. You still have to know how to calculate motion values because of that. Look at momentum. Momentum is mass times velocity. So if you have a ramp and I have momentum involved, well, how do I know what the velocity is at the bottom of the ramp without using some of the formulas for motion? Remember those three formulas? Let's see if we can remember them together. The final velocity equals the initial velocity plus AT, is that right? The final velocity squared equals the initial velocity squared plus 2AD. Is that right? Okay. What I'm doing is I'm actually at my computer, and I'm going to call that up, and I'm going to quiz you on this. Okay, did I give you the right equation, or what do you think? Remember, there's really three equations that are really important, and those two equations I gave you are correct, of course. Not of course, but who knows. So VF squared equals V naught squared plus 2AD. VF equals V naught plus AT. And then D, change in D, equals V naught T plus 1/2 AT squared. Now, if you're going to use in vertical, you're going to want to say T is Y and A is G. Okay? So those three equations will still be important for you. So I think we've covered quite a bit on fluids. So let's break away from fluids and see what's next here. I have fluids up until when an ice cube in a glass of water melts, the water level will. All right. Momentum now. I got momentum. So momentum, what's momentum? Momentum equals mass times velocity. What is change in momentum? Change in momentum is if you have a momentum because of movement, then you stop. What was the change in momentum? Now, the change in momentum will equal the impulse. Momentum doesn't equal the impulse. It's only a change of momentum, because what's impulse? Impulse is time. So the time it takes to stop, so to speak, would be impulse. The force and time, Ft. So you need a change in momentum in order to find your impulse, not just momentum. That's important. So there's really only a couple of equations for momentum. Remember the boat problem with Keith and someone else jumping off a boat? So you have the conservation of momentum, you have change in momentum, you have inertia. Well, who was Copernicus and what did he do? I see a question on Copernicus. You need to know everything there is to know about Newton's laws. Make sure you write down all of the equations regarding Newton's laws. Right from that the mass times gravity equals the weight. Weight is newtons. Now talking more about Newton's laws, don't forget the basic one, and that is that force equals mass times acceleration, and that is going to be Newton's second law. Newton's first law, again, is inertia, and third law is action-reaction. I think I'm going to quit, okay? And you'll be fine. I'll leave with one question, okay? And I won't give you any answers, and we'll see how you do. You ready? Okay. An unfortunate bug splatters against the windshield of a moving car. Compared to the deceleration of the car, the deceleration of the bug is. Also, what is the force exerted on the bug, and what is the force exerted on the car? And what does Newton's third law have to do with it? And then again, let's look at the acceleration. Okay? Good luck tomorrow. I just had a talk with some students from class, And make sure you can log on to Google Docs. So see the ICT people in the room around the corner from my office, across from the recording studio. And good luck tomorrow. Make sure you have, let's review what you need. For credit, 1 A4 piece of paper written on both sides. Has to be handwritten, not typed, handwritten. Make sure you have your second one for extra credit, A4 piece of paper written on both sides. You can write anything you want. Have something to write with. I recommend a pencil so you can erase. And then I don't give you anything. I don't give you any equation sheets or anything. Everything is on your own. Make sure you bring a calculator because you may not borrow one once you're in the exam room. Okay, so that's very, very important to understand. So make sure you have a calculator that works. If it needs batteries, put in some fresh ones. Don't take a chance. Okay? Take care. Good luck. I'll be here today if you're looking at this during lunch. And all the best. And goodbye.